This is lesson 2.8, fitting a model to data. This is like a continuation on lesson 2.7. So far in this chapter we have studied situations with two variables. However, in many real-life situations there are more than two variables. Consider the problem of determining the maximum weight that can be supported by a board. The three variables that influence the maximum weight m that the board can hold are the board's width, w, thickness t, and distance d between the supports. The goal is to find an equation relating w, t, d, and the dependent variable m, which we said was that maximum weight. By keeping all but one independent variable constant, you can investigate separately the relationship between the dependent variable m, so m is dependent, and that independent variable, the one that you're going to change and then the rest are held constant. To obtain equations that model these relationships, you can use the converse of the fundamental theorem of variation. So the converse. So the converse says, if multiplying every x value of a function by c results in multiplying the corresponding y values by c to the nth, then y varies directly as the nth power of x, that is y equals k times x to the nth. So that's that converse of that fundamental theorem of variation that we talked about in lesson 2.3. That's very important. Part B says if multiplying every x value of a function by c results in dividing the corresponding y values by c to the nth, then y varies inversely as the nth power of x. That is y equals k divided by x to the nth. So the converse is the opposite of that theorem. Go back to lesson 2.3 and look at that theorem. This will be the opposite. It's just flipping it around and saying it backwards, basically. So let's work through some problems on this, showing you how that the converse works for some different problems. So the maximum weight as a function of width. So now we're going to vary the width of that board and see how much maximum weight that board can hold. But we're going to hold that thickness and that distance the same. We're not going to change those. We're just going to vary the width. So Perry worked this problem and found a model by working with the variables two at a time. First, he held the two independent variables d and t constant. So I said there's going to hold the depth and the thickness constant. We're not going to change those. He did this by placing supports at the ends of 12-foot long, 1.5-inch thick boards of different widths. So now he's going to change the width only. He measured how much weight a board of a given width could support before it broke. He obtained the following data, and you can see the data in this table right here. So example 1a, verify that m, which is the maximum weight that board can hold, varies directly as w. So you want to verify that m equals k times w. Well, we're just going to follow those steps that we learned in lesson 2.1 and 2.2. So step 1, we wrote our general variation equation. Step 2, let's plug in some points and see what we get for k. So we're just going to pick the width 1 and the m of 9. So 9 equals k times 1. We're going to solve for k. We're going to divide both sides by 1. K equals 9. Now step 3, we're going to write that variation equation. M equals 9w. Now in step 4, we're going to see if all the rest of these data points in this table work for that variation equation. So we're going to test them. So if we take the next one, width equals 2, our m should be 18. And that's what it is here. We'll test the next one. If width is 3, we're checking the 3. M should be 27, and we get 26. It's pretty close. It just has to be pretty close. We can go on. If our width is 4, 4 times 9, because our k value is 9, our m should be 36, which it is. If width is 5, 5 times 9, our m is 45, and it's 44, so pretty close. And finally, if width is 6, 6 times 9 is 54. That's pretty close to 53. So definitely looks like with this data that M does vary directly as W.